Okay, shall we get started? Sounds good. Let me reduce the volume a bit. Okay, that sounds better. Okay, today we will wrap up cache coherence, which we started, but just to jog your memory, we covered a lot of multiprocessing yesterday, a lot of fundamentals, as well as advanced concepts, and then we spent a lot of time on memory ordering, or the consistency model, and then we started cache coherence, and we made a good dent into it. Today we'll finish what I have in mind, and then after that we will have a review session. And then we can discuss the logistics of it when we get to it. But let's finish cache coherence first. As I said, there's a lot of work in this area also. It's another exciting topic. And coherence is a very general concept that exists everywhere in systems. Whenever you replicate data, you have to keep it coherent somehow. That's a given. And nothing is different in multiprocessors. Okay, again, to jog your memory, we were discussing Snoopy bus-based protocols and then directory-based protocols. We discussed a very simple Snoopy bus-based protocol. Basically, these assume that you have a single point of serialization for all memory requests. You have a bus, basically, that connects all the processors, and whenever a processor does an action on a memory location, it broadcasts that action, and everybody on the bus observes that action, and they can, based on the protocol that's implemented, they can take an appropriate action based on the action it observes on the bus. This is nice because you have this shared bus, right? Directory, on the other hand, doesn't assume anything like that. It's really independent of the interconnect, if you will. But it assumes a single point of serialization per block. And this could be distributed among nodes for different blocks so that you can achieve high scalability. Every access goes to the directory for a given block. So you make explicit requests, and directory is the mediator, essentially. And we covered this in more detail yesterday, so I'm not going to go over this again. So you remember my beautiful handwriting. It used to be better when I was in high school. Okay, but we stopped here. We're going to get back to the directory. But essentially, you can think of the directory as a coordinator for all actions that are to be performed on a given block by any processor, right? It's the middleman. And its job is to really guarantee correctness and ordering. And given its simplicity, it does have that guarantee, right? Every request goes through it, it's serialized over there, and then it requires acknowledgments from different processors before it takes another action. So clearly there's overhead involved in this also. And as a result of this, there are many opportunities for optimization because the directory has a global knowledge about each block. So it can actually tell, you can, for example, bypass the directory and directly communicate between the caches with some information. Maybe the directory coordinates that, but also you could potentially cache the directory at some places, right? So because, as we will see later on, directory becomes big and very big if you have a scalable multiprocessor system. And in modern systems, directory itself gets cached close to the nodes. That's interesting, right? Now, how do you keep the directory coherent? Becomes interesting also. But that's essentially a problem with the directory. How do you make it fast to access? And we will see examples of the optimizations later, although I've already told you that directory can say, because directory has global knowledge of the system, it can say, oh, cache X, you have the copy of this block A, so please send it to cache Y. And don't send it to me because I don't really need it. Right? You can make that sort of optimizations. And you could actually adapt those optimizations to the traffic patterns if you actually know them, but certainly to the interconnect, because directory should have some knowledge about how where different processors are in the system. So if two processors are close to each other, maybe it makes sense to tell them to communicate a cache block, a requested cache block between each other without disturbing anything else in the system. Right. Okay. Any questions on directories? Okay, let's move back to Snoopy cache coherence, and we'll discuss some protocols. By the way, these are mechanisms. Directory and Snoopy cache coherence, these are different mechanisms. It's really about the serialization of the blocks. But protocols themselves can be essentially similar. For example, the MESI protocol we will discuss, or valid-invalid protocol we will discuss, applies to both Snoopy cache coherence or directory-based cache coherence. You can implement the same protocol under different mechanisms. Right? Those really dictate the states the cache block can be in, and those states can be changed based on having a single point of serialization for everything based on a bus, or going through the directory, right? So you could actually have different protocols, same protocols implemented on these different things. And we will see an example. Okay, the idea of Snoopy cache coherence is we've seen before, but more formally, all caches essentially snoop all other caches' read and write requests and keep the cache block coherent. And by the natural way of thinking it is having a single point of serialization like a bus. Each cache block has some coherence metadata associated with it in the tag store of each cache. So now you're adding the coherence metadata into the caches as opposed to the directory. Remember, in a directory-based scheme, you may actually need some coherence metadata like the exclusive bit or private bit, right? But now we're going to add a lot more metadata into the cache because there's no directory to keep this metadata anymore. Okay, and this is easy to implement if all caches share a common bus, right? Everybody broadcasts their requests. That's what I said. So it's good for small-scale multiprocessors, but how do you scale it if you would like to have 1,000 nodes in your multiprocessor? This may not be that easy, and as a result, many systems today have both directory-based and bus-based cache coherence, or Snoopy cache coherence, in their designs. They're more hierarchical coherence mechanisms. Okay, so this is another picture of this. Basically, this is our shared bus, and you have processors and caches attached to it. And each cache, we're going to add coherent state bits in the tag store. And we will see examples of this. For example, one example will be the MESI protocol, which has 4 states per cache block. And I think I already said all of this. Each cache observes its own processor and the bus, basically. It has requests coming from the processor, and it has requests coming from the bus. And it can also put requests onto the bus, each cache, based on the actions taken by the processor. And it changes each cache changes the state of the cache block based on the observed actions it has from the processor as well as the bus. So it's nice, as you can see. So there are 2 processor actions to the block, we're going to assume, for now. Basically, the processor can do a read to a block. That's the PR, as we've seen earlier, processor read. And the processor can do a write to a block. That's the processor write. And these translate to actions on the shared bus. So whenever the processor does a read to a block, the cache sends a bus read on the bus. And any other caches who observe that bus read take an appropriate action depending on the state of the block in their tag store. And whenever the processor does a write to the cache block, the cache sends, assuming it's not an exclusive state, if you have an exclusive state or a modified state over here, the cache sends a bus write request on the shared bus. And everybody else, or bus write, as we said yesterday, bus write is also called bus read exclusive. Basically, you want to read the data in an exclusive state because you're going to write to it. In different cache protocols, you will see different names for it, but the common term is really read exclusive. You want to get exclusive access to the block because you're going to write to it. And if the processor requests a write, then the cache sends a bus read exclusive request that's broadcast on the shared bus, and depending on the state of the block that's being requested exclusively by this cache, every other cache takes an appropriate action. And what is an appropriate action is really determined by the protocol. You can have many different protocols of different complexities, right? So let's start with simple protocols. We've seen this protocol already. This is the valid-invalid protocol, VI protocol, right? It assumes some things about the cache. It's a write-through cache. You don't allocate on writes. That's how the state diagram works. Basically, whenever you observe a bus write on the bus, if you're in valid state, you move to invalid state, right? And valid state has a meaning here, right? Valid state means that you have the copy, and the copy is clean. Clean meaning it's the same as the copy in memory. Why? Because we're assuming a write-through cache in this case. So each state has a meaning, and you've got to ensure that that invariant meaning the invariant is always kept constant. Otherwise, you'll get a violation and you'll get wrong results, right? Okay, we've seen this protocol. This is a simple protocol. Okay, so this protocol clearly assumes a write-through cache. What if we don't want that, right? Because we don't want, there are many reasons why we don't want a write-through cache. It has a lot of bandwidth that's exposed to the bus. If you want write-back caches, we want a modified state clearly, or dirty state. We'll call it modified in this case. And a more sophisticated protocol is the MSI protocol, modified, shared, invalid. So it has 3 states. We extend the metadata per block to encode those 3 states. So, and then you have invariants in each state. If a block is modified, that means that the cache line is the only cached copy here in this processor, and it is dirty. So essentially, you have exclusive access to it, right? Shared means cache line is potentially one of several cache copies, and it is clean. It may be the only copy, but you don't know that. Potentially, it's one of the several cache copies. But it's clean, meaning that the copy that this processor has, the block in the shared state in its cache, is the same as the copy in memory. And if some other cache has it, those are all same copies. So you can actually, all of the processors can read without notifying each other, right? So invalid means cache line is not present in the cache clearly, right? If you don't have a block, then it's invalid. So if you have a read miss in the cache, that translates into a read request on the bus, and the cache transitions into a shared state after that, right? Because there's no other state, as you can see. You go from invalid to shared. If you have a write miss, the processor gets a write miss, then the cache makes a read exclusive request, and that read exclusive request invalidates everyone else, and the cache transitions that block into the modified state. Make sense? Now you have that block, and you can modify it without telling anyone. And when a processor snoops or sees a read exclusive request broadcast on the bus from another cache, it must invalidate its own copy, if it has any, right? So it goes from one of those states, either modified or shared, to invalid state. Now you have a potential for optimization, right? If you're a modified state, how do you transition to an invalid state? Well, you'll need to supply the data, certainly, because you have the data. Do you supply to memory as well, or do you do a cache-to-cache transfer directly? So even this has optimization opportunities. I haven't defined the term upgrade or downgrade, but upgrade means you go to a state where you have more permission to operate on the data, right? Exclusive state, for example, or this doesn't have an exclusive state, but you can think of modified as you have the exclusive copy of the data and it's dirty in your cache. But in that state, you have the highest level of permission. So going from shared to modified means you're upgrading your permission levels, right? Because in the shared state, you cannot write to the data. You have to upgrade your permissions to the modified state. So when you go from shared to modified, you can actually, you don't need to reread the data from memory, because you know that the copy you have is up to date and it's clean. It's the same as memory. So as long as you invalidate, as long as the protocol ensures that all of the other caches are invalidated, you can directly transition from shared to modified. Right? That's obvious, hopefully. Okay, and this is the state diagram for the MSI protocol, as you can see. It's more complicated. Let's see what I want to show over here. But let's take a look over here. For example, if you want to go from shared to modified state, the processor, if you're in shared state, if this block is in shared state and the processor wants to write to it, the cache sends a bus read exclusive on the bus. And everybody else, when they get the bus read exclusive, for example, over here, if somebody is in modified state, they get the bus read exclusive, they go into invalid state and they flush the data. Meaning they move the data to memory, for example, right? Or you could do a cache-to-cache transfer at that point. So if somebody's in shared state, and if they get a bus read exclusive request, they go to invalid state, but they don't need to do anything because it's in shared state, right? The data is up to date in memory, right? But you could, of course, optimize this protocol also, right? If the shared state and you want to do a cache-to-cache transfer. Where do you get the data is not encoded over here necessarily in this. This just shows how the state of a block changes. This doesn't tell anything about where does a processor get the data from, right? Make sense? So you could actually optimize that. But you may need to add more states, of course, to ensure that you don't go into some... so even though this looks conceptually nice, there may be some intermediate states that you may need to add, waiting for the block, for example. We discussed this briefly yesterday. There may be race conditions that may happen while you're waiting for the block to come. So this is conceptually nice, but what's implemented usually has a lot of intermediate states while you're waiting for the block to come from memory, for example, or from some other cache. But we'll keep it at the conceptual level over here. If you actually really implement this in a real processor, it becomes more complicated. Okay, so for example here, if a block is in shared state in your cache, and if the processor wants to read it, you don't need to do anything, right? You can just read the block. You don't send a request out to the bus. If the block is in the shared state, and if somebody is actually reading, you get a bus read request, you don't need to do anything again. Which means that some other cache doesn't have the... if you see a bus read request, that means that some other cache doesn't have the block in its cache, so it's putting out a bus read request. And this is shared, so it's a clean copy. So that cache can get the block itself from memory, right? Or from some other cache. Okay. Another example over here is you're in modified state and you see a bus read request. This means that this cache itself has the only copy exclusively, and somebody else wants to read that copy, which means that this cache needs to flush the data to memory such that the other processor who wants to read it gets the data, and this processor needs to move to the shared state. And that's a design choice, right? Why did we decide to go from modified to shared over here when we see that somebody else is reading it? We could have decided to go to invalid state. This depends on the sharing pattern potentially, right? Okay, so even this is not a protocol that's golden. It really depends on the design choices somebody has made. Okay. Okay, there are problems with it also. Any questions on this? This is clear, hopefully, right? Yes. So one problem with MSI is a block is in no cache to begin with, right? Initially, every cache has the block in an invalid state. But on a read, the block immediately goes to the shared state because there is no other state that we have. Although it may be the only copy that's cached. In fact, the first processor that reads the block is the one who will have the only copy that's cached. And no other processor may later cache it. Right. See the problem with this? Basically, well, why is this a problem? First of all, suppose that the cache that reads the block wants to write to it at some point. What does it need to do? So when we read the block A, we sent out a read request to everyone else. No one else has it. We got the block. Block is in shared state. Shared means that I have the block, but somebody else may also have the block also. Right? Now, if you want to write to it, even though you may have the only copy, you don't know that. So you have to broadcast an invalidate request. Just because you don't know that you have the only copy in the system. Right? And as a result, but if the cache actually knew it had the only cache copy in the system, it could have written to the block without notifying any other cache. Right? So if you actually had this information encoded in the states for the block, you would have saved unnecessary broadcast of invalidations. And this may happen a lot, actually. You may actually get a block to read. You do some stuff to it, and then you write to it after some point. But when you write to it, because it's in shared state, you need to broadcast invalidations, and it's a waste. You need to wait for those invalidations to be acknowledged at some point. Well, in the bus, there's also some states over there that we're not talking about. But basically, it's a waste, even though that's the only copy in the system. Make sense? So how do you solve this problem? The problem is actually easy to solve. That's the idea of the MESI protocol. Basically, we add another state indicating that this block is the only cached copy in the system, and it's clean. Meaning, this processor has the block, and it's the only copy in any cache, and it's the same as the copy in memory. It's called exclusive clean, or it's called an exclusive state. And block is placed into the exclusive state when you actually do a bus read. You send out a bus read request, and you somehow figure out that no other cache has it. Then you transition from invalid to exclusive state, as opposed to going from invalid to shared in MSI. And how do you actually figure out that no other cache has it? Well, one way of doing it is having a wire door signal on the bus. Each cache, if it has the copy, then it will assert that signal. And if the wire door is 1, then you know that somebody else has the copy. If the wire door evaluates to 0, then you know that no one else has the copy. Now you can transition to exclusive state. Okay. So now we've enabled, if the cache later wants to write to that block, you can silently go from exclusive to modified without notifying anyone. There's no need for invalidation because you know that you have the only copy in the system, other than the memory, of course. Okay, this is also called the Illinois protocol because it was developed at University of Illinois by Janak Patel and one of his master's students. It's a beautiful paper that I recommend, actually. Okay. Well, I guess I'll show the state diagram in my own pictures. But basically, these are the requests that we've talked about: processor read, processor write, and these are the bus read, bus write. And bus write can be bus invalidate. So this is another way of thinking about the protocol. You can invalidate, but you already have the data, so don't supply it. And there's also bus read invalidate, which is you can invalidate, but also need the data. So you need to supply it somehow to the processor. Okay, so these are the 4 states. Actually, it's better to say it over here. So modified state, so invalid state is obvious. Shared state still has the same meaning. It's shared. It's potentially shared. Again, we don't know. Because of the invalidations, you may still have the only copy in the system, but you may not know. You need an additional mechanism to know that if you're going from shared to exclusive. We're not going to do that over here. But shared, in this case, the meaning is it's potentially shared. It's potentially present in multiple caches, but it's clean. The same copy as in memory. Exclusive means that it's present only in this cache, and it's clean. Modified means that it's present only in this cache, but it's modified. So clearly, you could potentially have another state. You could have another state, but we'll get to it. Okay, so this is the state diagram with the new terminology that I have over here. This is invalid, exclusive clean, exclusive modified, and shared clean over here. So for example, if the processor wants to read an invalid block, it doesn't have, it sends out a bus request, and it figures out it's the only processor that has the block, or that's requesting the block in the cache, and no other processor actually has that block. So it directly transitions into the exclusive clean state. This is another, okay, let's look at this one over here. So what this enables, let's look at this one actually. What this enables is if the processor wants to write to the block in the exclusive clean state, it can go to the exclusive modified state without telling anyone. It doesn't need to send any action to outside. So if the processor is in an invalid state, and it wants to read the block, it sends out a bus request, bus read request. If some other cache has it, if that wired OR evaluates to true, it needs to go into the shared clean state. Right? Make sense? Okay. Okay, and you can follow this diagram over here. It also says when do you need to supply the data to the processor and when do you not need to supply the data, ... Okay, this is another view of it. It says nicely MESI over here. But basically, I highlighted the same transitions over here. You can write to a block. If you're in exclusive state, you can write to a block silently. And the way you go to exclusive state is over here. When you read, you send out a bus read request, and no one has it. And when you read, you send out a bus read request, and someone has it, then you transition into the shared state. Okay. And if we had a Lab 5, probably we won't have time for it. But if you take this class in the future, you will probably have a Lab 5, and that is the state machine that you will implement if you happen to take in the future. And you're welcome to study this. But the reason I have it over here is I want to define the downgrade and upgrade a little bit more, even though I defined it briefly. So a transition from a single owner state, exclusive or modified, you have higher permissions, to shared is called a downgrade, because the transition really takes away the owner's right to modify data, right? You're downgrading your permissions. And a transition from the shared state to a single owner state, exclusive or modified, is called an upgrade because the transition grants the ability to the owner, i.e. the cache which contains the respective block, to write to the block. So that's higher permission versus lower permission states. And yeah, we can have fun with the state machine that we have in Lab 5. Okay, so this is actually what's implemented in Intel Pentium Pro, which is the first processor that was very heavily successful in employing out-of-order execution. Essentially, you can see exactly the same thing, right? I'm not going to go through this again, but maybe some of the design choices are slightly different, because you can actually have different design choices. Okay. Okay, let's talk about the trade-offs of the Snoopy invalidation a little bit. One thing that I've briefly talked about is, should a downgrade go from modified to shared or invalid? That's a design choice, right? Basically, if the data is likely to be reused before it's written to by another processor, maybe you should go to shared. If the data is likely to be not reused, maybe you should go to invalid, right? You're in modified state. Do you keep the data after someone else requests it, or do you not keep it? Right. That's the key question over here. All of these choices really depend on the sharing patterns, and you can actually complicate the protocol if you want to take into account sharing patterns dynamically. You dynamically figure out that whenever somebody else requests the data, this particular block, let's say, when you're in modified state, somebody else is going to write to it later on, so I'm going to get an invalidation. So there's no point of transitioning into the shared state. I might as well go to invalid right away. Right. That way I'll at least save some cache space, and I can bring some other data into that block that's invalid. That's a free block that I have in the cache, right? So if you can take into account those sharing patterns, either dynamically or statically with hints, you can do better. But then all of these complicate the protocol now, right? Now you have different transitions, different things that you need to take into account. How do you do that? Okay, so cache-to-cache transfer, we've also talked about, right? On a bus read, should the data come from another cache or should it come from memory? Again, that's a design choice. That doesn't get encoded always in the state diagrams. But there's a reason why you may want to get it from another cache, because it's maybe faster. This may be faster because of the distance between the caches, or because the contention, right? Memory may be much slower than some other caches, which is usually the case. Or memory may be highly contended, or some other cache may be highly contended. So depending on those patterns, you may want to adapt. And that complicates now your design, right, if you want to adapt. If you get it from memory, it's simpler. Basically, you send out a request directly to memory before waiting to see if another cache has the data first, right? Maybe you have some other path, right? And this also creates less contention at the other caches. But if you want to get it from memory, this requires write back when you have a downgrade from the modified state. So basically, that's this side over here. When you go from modified to shared, do you really need a write back? This depends on whether you're getting the data from memory, right? Okay, so we'll discuss this in a little bit, basically. One possibility is to actually extend the state such that you have an owner, and one cache owns the latest data, and you don't update the memory, and write back happens only when all caches evict their copies, or when the owner evicts its copy. So let's take a look at the problem over here. The problem with MESI, one problem with MESI is shared state requires the data to be clean. So we're dissecting each of the states now. Which means that all caches that have the block have the up-to-date copy, and so does the memory. And you need to keep that invariant to be correct. But the problem is, you need to write the block to memory when bus read happens when the block is in modified state now. So you're in modified state, and somebody's reading the data, right? You have the only copy. Well, you have the exclusive clean copy, which is the only exclusive dirty copy, which is the only copy. Now you have to write it back because you need to go to the shared state. That's the only state we have. And the shared state semantic says that all caches that have the block have the up-to-date copy, and so does the memory. So what you cannot do with this semantics is have two caches in modified state, right? Because we don't have a state for that. And that's the idea of the MESI protocol. Well, why is this a problem, first of all, right? Basically, memory can be updated non-necessarily, right? So this cache has this block in memory modified state. Somebody else wants to read it. The natural thing that you would think would be both of the caches have the block in modified state, and memory doesn't have the up-to-date copy, right? Now, both of the caches may modify, invalidate, do whatever, without writing to memory. But we don't account for that in the MESI protocol because there is no such state that says memory is not up to date, but the data is shared across caches, right? So, which means that you have to update memory unnecessarily if somebody has modified the data and somebody else requests that modified data. There may be no need. This is actually a ping-ponging issue, right? If you're actually ping-ponging the data, you have a shared lock, somebody writes to the lock, it's a modified state. Now somebody else wants to acquire that lock, it sends a read request. And it's going to write to that lock at some point, perhaps. It's trying to check the lock, right? It sends a read request. The data gets supplied, but the data has to be written back to memory also. So you cause unnecessary traffic, even though this other cache that requests the block is going to write to that block later on to acquire the lock. And then this happens to some other processor also. Now it's a modified state on this processor Y. Now processor Z wants to get the data. It sends out a read request, and it gets the data, but memory has to be updated also because of the semantics we have for the shared state. So because of this ping-ponging of the locks or shared data, you update memory unnecessarily many, many times. And as a result, MESI has this problem. So how do you solve the problem? Basically, there are multiple solutions to the problem, actually. One solution is this, basically. Do not transition from modified to shared on a bus read. Invalidate the copy that you have. You get a bus read. You invalidate the modified block that you have and supply it directly to the requesting processor without updating memory. Now, this may help ping-ponging, right? You actually transition the modified permission from this cache to this other cache. Now, that actually solves the problem, but that complicates things a little bit. Now, you have to definitely have a cache-to-cache transfer over here. But it's certainly a solution to the problem. Another solution that's used in some processors is the MESI protocol. Basically, transition from M to S, but designate one cache as the owner, who will write the block back when it is evicted. So basically, we're really changing the semantics of the shared state now. Now, shared means, before shared meant shared and clean, right? Potentially shared, potentially in multiple caches, and clean. Now shared means shared, i.e. potentially in multiple caches, but it's potentially dirty. Right? And this is a version of the MESI protocol, for example. There are many versions of it. But whenever the owner evicts the data, there needs to be some special action taken. So owner is another state, essentially. Why don't we have 5 states? Right. The owner needs to somehow evict the data. And you need to have different actions, of course, because now your shared state means something else, right? The data is potentially dirty. Does that make sense? Okay, we're not going to cover this in a lot of detail, but a lot of existing systems implement the MESI protocol because of this problem that we just discussed. You unnecessarily update the memory. Okay, any questions? Now, we could keep doing this, adding more states and making the coherence protocol more and more complicated. But basically, you can have more sophisticated cache coherence protocols. You can optimize it with more states and prediction mechanisms to reduce all of these unnecessary invalidates, unnecessary transfers of blocks, unnecessary write-backs to memory. That's the upside of making your coherence protocol more complicated, right? you minimize traffic, and you hopefully get better performance as a result of that, and better energy consumption. However, as you add more states and more optimizations, the protocol becomes more difficult. Also, all of those things become more difficult to design and verify. Now you need to keep track of more cases and race conditions also, because you need to ensure that while you're waiting for the data, somebody else doesn't get permissions, right? And that leads to all of these additional states. Even though I showed you nice 4 states, it may actually be, I don't know, 10 states in real life, because there are a lot of internal states, intermediate states, going from one logical state to another logical state to handle the race conditions. And as you add more states, the state space explodes. As a result, this becomes very hard to design and verify. And also, you get diminishing returns on top of that, right? The big returns, going from valid to invalid to MSI buys you something big. Going from MSI to MESI buys you something big. And going from MESI to MOSI buys you something big, but those bigs are increasingly smaller. As a result, maybe you don't get much benefit, although you may have a lot of headache to get this correct. And if you actually look at the errata of existing processors, a lot of the bugs are in the coherence protocol. Now, they don't tell you exactly what it is, because they could potentially be exploitable for security attacks, right? But a lot of these bugs, the difficult bugs that are difficult to fix, happen to be in the coherence protocols, if you read the Intel errata, for example. Okay. So this is what we've covered basically so far. We'll look at some more optimizations, now that we've covered both of these designs, let's do a trade-off analysis. We have the Snoopy cache versus directory coherence. And as I said, directory coherence can also implement the MESI protocol. The directory itself guarantees some of those protocols, right? Directory coherence can implement the valid-invalid protocol also. Snoopy cache can implement any of the so protocol is really independent of the mechanism itself. Although directory coherence enables more simpler implementation potentially, right? Okay, so Snoopy cache, the big advantage is your missed latency or critical path is short. You send a request, it's essentially a bus transaction memory, and you get the result. There is no middleman. There is no intermediary, which is the directory in directory coherence, right? So you can quickly get the data. And global serialization is easy because the bus provides us already, right? And it's a natural point of arbitration. It's simple. You can adapt bus-based uniprocessor easily. So you can have one uniprocessor that has a bus to memory, add another processor, another processor, another processor, and that's simple, right? You just need to add some state into the caches. So the downside is it relies on broadcast messages to be seen by all caches and also in the same order for a given block, right? So how do you satisfy this? With a bus, this is easy. But the problem with the bus is it's not scalable, right? That's one of the reasons why we will cover interconnects as the next lecture, because it's very tightly integrated with the scalability and the coherence protocol as well. If you want to, let's say, add 1,000 processors on a single bus, good luck with that, right? You may need to make the bus really, really slow. But then that actually goes against a scalability, right? So basically, as you add more processors on the bus, there are multiple issues. One is certainly the loading. Electrical loading on the bus increases. And as a result, the reliability reduces. So you'll need to take actions to make it reliable, which comes at a cost of latency and frequency and ... And also, as you add more processors on the bus, if you want to give the illusion that everybody sees everything, now there can be only one request on the bus, right? Now that also is another scalability bottleneck if you have a single bus. If you have multiple buses, then you don't have a single point of serialization anymore. Okay. And so basically, you somehow need a virtual bus if you want to make it scalable. Meaning that you have a totally ordered interconnect that looks like a bus. And this is actually a tough thing to do. How do you actually, for example, if you have a two-dimensional mesh or torus interconnect, which we will talk about later, how do you actually give the illusion of Snoopy cache coherence on that? Because by definition, Snoopy cache coherence, in a sense, assumes that you have the single point of serialization for all requests. Okay, so we may talk about that later on. Okay, directory, to be consistent over here, basically the big disadvantage is it adds indirection to the missed latency, right? So you have one more hop to go through, and perhaps other mechanisms like the acknowledgement. So directory is basically slow. You add stuff on your critical path. The request needs to go through the directory, and then the directory supplies the data, or tells you how to get the data, or tells someone else to give you the data. Right? So that indirection is costly in terms of performance. And it requires extra storage space to track share sets in the directory. So directory space can be actually much larger. Actually, there was one past question that we had in homeworks and exams which looked at how you compare the state, how much state you need to keep track of in a MESI protocol in the Snoopy cache versus in a directory protocol, right? Here, the state is kept track in the caches, right? Each cache block has, in the MESI protocol, 2 bits. In the MESI protocol, 3 bits, assuming no intermediate states, again, per block. But that's small compared to the directory, because in the directory, you need to keep track of the entire physical memory. Every single block in the physical memory needs to have some directory stored saying, where is this block? Even though nobody has a block. Right? You may have only 2 shared blocks in the system, yet the directory needs to keep track of everything in physical memory. Right? So this is actually expensive, and we'll do a calculation at the end to look at that. So that's the trade-off, basically. Where is the storage space and how big is it? But you can also make it potentially approximate. We'll talk about that, because you don't need to have perfect tracking of sharing in some cases, right? You can have extra invalidations. Right? If you don't know all of the shares perfectly, you can invalidate everyone in the worst case, right? And wait for acknowledgements. Of course, that's bad for traffic, so this is a trade-off between storage versus bandwidth now. You can reduce your storage at the expense of additional invalidations, additional bandwidth consumption. Because false positives may be okay. The directory may think that, oh, this cache has the block, but that cache doesn't actually have the block. It doesn't hurt to send an invalidation request to that cache from correctness point of view. And that cache says, oh, I don't have the block, so I have nothing to invalidate. Right? But, of course, that costs additional acknowledgements and invalidations. So the invalidation traffic is still a problem in the directory. That is really a protocol issue. And protocols and race conditions may be more complex if you want to get high performance, because now the directory needs to mediate what's going on in the system. Whereas if you really have a single bus, you know what's happening every cycle on the bus, and you can actually make things a lot more simpler. Whereas the directory now needs to keep track of many, many things, right? I think somebody pointed out yesterday that what if multiple caches request the same block? What if 1,000 processes request the same block at the same time, right? What does the directory do? Buffer all of those requests? Now you have storage space that you need. A bus eliminates all of that buffering, right? A bus, you need to arbitrate. Let's assume you have 1,000 processors. One of them wins, and it broadcasts what it wants, right? That's it. Whereas if you have a directory, now the directory has a choice. I can knack the core that's requesting this block. Knack means negative acknowledgement. I can say, sorry, you're not getting the block because someone else is also requesting it. Or I can buffer these requests and maybe serve them in order after some point. Both of them are complicated. But the big advantage is it doesn't require broadcast to all caches. Clearly, you have more space for optimization over here, right? Even though you may require more complicated protocols, you get rid of that broadcast. And if you actually have a directory and if you're broadcasting all the time, then you're probably doing something wrong. Okay. And the other big advantage is it's independent of your interconnect now. You don't require a bus, physical bus, or you don't require a virtual bus, somehow an interconnect that emulates the characteristics of a physical bus. You don't require any of that. Your interconnect can be anything, right? As long as everybody who needs to modify a given block is able to reach the directory for that particular block, right? not modify, modify or cache that. And as a result, you can be much, much more scalable than the bus. Your interconnect can be arbitrary. Okay? So those are the trade-offs, basically. Any questions? Maybe there are some other thoughts on this. Okay, good. So existing systems actually have a combination of both. Directories are complicated, and people actually have hierarchical directories. People cache the directories at different places. As long as, for example, you know where you cache the directory, you limit the place. You know exactly the directory can be cached only in this node. Then you actually don't need to have coherence in the directory, right? Because you have a home node and a home cache for the directory, for a given block. Okay, so let's revisit the directory-based cache coherence a little bit more. Let's talk about some of the optimizations. And I'm not going to go through this because it's essentially what we've covered in the directory-based cache coherence. Remember, we had this p+1 bits in the directory for each cache block. For each possible cache block. This is not for each cache block that's in the cache, right? This is really for each possible cache block in memory, in physical memory. And remember, we went through this diagram before. But basically, these are really required if you want to scale past the capacity of a single bus. It's not easy to keep the Snoopy cache coherence. There have been attempts to keep the Snoopy cache coherence without a single bus, but it's still a research topic, actually. This is naturally distributed, so you can distribute the directory, as we said, right? You can have 1,000 nodes, and each node can be responsible for 1/1000th of the physical memory address space, and keep the directory for that portion, right? And each node each node basically serializes the requests for that part of the memory. So coherence still requires single point of serialization, and that's what the directory does. But serialization location now can be different for every block, right? You can stripe it across nodes or memory controllers. And people have actually proposed mechanisms for dynamically migrating the directory entries for different blocks. So you could actually exercise a lot of creativity here with additional complexity, of course. Right. But one simple mechanism is statically partitioning your directory for different blocks in physical memory in different nodes. So if you want to access address 0, you know that you need to go to node 0 to get the permissions. Okay. But now you can actually reason about the protocol for a single block. This is really a client-server communication model, right? You have one server, which is a directory node, that holds the directory entry for that block. And you can have many clients, the private caches. And clients essentially request permissions from the server to manipulate that block in some way. And the manipulation is done with requests, read and exclusive requests. Directory receives these requests and sends invalidation requests or other requests. So in this case, invalidation is explicit. You send explicit invalidation requests as opposed to Snoopy buses, right? Snoopy bus coherence. Each cache implicitly invalidates, and nobody else may know. But here, the directory is controlling everything. So that opens up a huge space of optimization. Okay, let's look at, and we'll see examples of this maybe. But let's look at the data structures also, because these could get pretty large. So this is one example of a directory, for example. For this block, you keep the share set. This may be different from the p+1 bits. So p+1 bits is an abstraction that basically perfectly tracks which processor has which block, plus which processor has it in exclusive state, right? You don't necessarily need to do that, right? Maybe your p+1 bits, you can encode this shared, if this block is shared by processors P0, P1, P2, maybe you could encode it in a different way. So assume that you have, 10,000 processors in the system. Are you going to have 10,000 1 bits for each cache block, potential cache block? If you have only one share, that's a huge waste, right? Maybe you just have a pointer to the share. And maybe you have a limited share set. You keep track of only 3 shares, and after that you resort to invalidating everyone. May not be a good choice. But if you never overflow the number of shares that you keep track of perfectly, that may be an okay choice. Right? Okay. Basically, a key operation to support is a set inclusion test, meaning you get a request and you need to figure out who has the block, in what state. If the directory says a block has the block, a private cache has the block, but the cache doesn't have it, then that's okay again. The directory sends an invalidation request, right? Basically, we want to really know which caches may contain the copy of block, and you can send spurious invalidations because of false positives in this case, but the caches ignore those invalidations. So you just waste some bandwidth. So that way you can trade off the storage space with additional bandwidth, as we've discussed. But of course, false positive rate determines performance now. Right? So now you could actually optimize the space. So as we said, the most accurate tracking mechanism and expensive tracking mechanism is having a full bit vector, 1 bit per each processor, essentially a 1-hot encoding for every cache block, plus 1 exclusive bit. Exclusive bit is really important because of what we discussed, right? Going from MESI and MOESI, going from MSI to MESI buys you a lot of performance, even though I didn't show you. The paper that you're reading talks about that. If you have an exclusive bit over here, you enable silent updates to the block. So you have a full bit vector plus 1. But you could also have compressed representations of this, linked lists, maybe, Bloom filters. Those are some good topics that we've discussed, right?
Hallo, sprechen Sie Deutsch?
Somebody's talking to us. Hello?
Also sprechen Sie Deutsch?
Can you hear us?
Hello?
No?
Also Sie sprechen kein Deutsch, oder?
No. Does anybody speak?
Wir sprechen Deutsch.
Ach so, okay. Also wir sind vom Forschungsinstitut GFS in Bern. Wir machen eine repräsentative Umfrage zum Thema Gebühren in der Schweiz. Vielleicht hätten Sie auch etwa die 9 Minuten Zeit.
We can hang up? Where we hang? So how do we hang up?
Ach so, okay. Dann wünsche ich Ihnen noch einen schönen Tag noch. Ne? Goodbye.
Okay. How did we even join this? Okay, they're hanging up. Somebody else called it then. Okay, we have a security problem here. Interesting. Anyway, we'll figure this out later. I didn't call anyone, right? I don't remember. Unless this is a mind of its own, then. Okay, but basically you can optimize the storage space at the cost of additional bandwidth. And actually existing systems employ some of these techniques. But we're not going to go into that. So let's look at the basic operations. Essentially, we really, as I said, protocols are similar to the Snoopy-based system, right? But you're really doing everything explicitly now. You have an explicit request and reply messages sent to the directory. As we said, you receive read exclusive upgrade or many different potential requests from different nodes. And you can send invalidate, downgrade messages to shares if needed. And you can forward the request to the memory if needed, or you can mediate the request coming from memory. And you can reply to the requester and update the sharing state. And you can have many, many other actions over here, right? Because the protocol design is really flexible. It's really up to you now. You can, for example, as we said, exact forwarding path depends on the implementation. Maybe the directory instructs a cache to send a block to another cache, right? Or maybe a directory instructs a cache to send a block to 4 other caches. That's called a multicast operation, right? If you have this information stored in a place about a block and who's requesting it, the directory can keep those requests, aggregate them, and say, oh, 4 other caches requested this block, and they want it in shared state. They're all going to read it. So cache X, you have it in modified state. Why don't you multicast or send that block to everybody else who wants it? So it's very simple, though you cannot do these things in bus-based protocols, Snoopy protocols. Okay, let's look at some examples. This is processor 1 sends a read request. This is the directory node for a block that's being read is called the home node for that block. It's the home node in the directory. It could be anywhere in the system again. So you send a read request, and the directory sends the data exclusively or shared in a manner. But the directory also can say, when you get a read request from P0, the directory can tell P1, P1, you have the block, so why don't you send it to P0? Right? So it's very flexible. Let's look at another example. This processor 0 wants to do a read exclusive request. It sends a request to the home node for block A, let's say. The home node knows that some other processor has the block. It sends an invalidation request. And the owner sends, OK, I have invalidated, or maybe a revised data also gets sent to the directory. But in this invalidation request, the directory may actually include a message saying that, oh, by the way, while you're invalidating your data, send it to P0, right? And P0 may get that data. So it's really, whatever you encode in the messages can get communicated easily, right? It's a very flexible protocol design. And this is another example. This is the example that somebody brought up yesterday. Basically, if both processors want to write to a block, they both request it in read exclusive mode. And the directory may arbitrarily decide, oh, processor 0 gets the block, and send a NAC request or NAC response to processor 1 saying, too bad, you're not getting the block. Now, clearly, we're onto fairness issues here, right? This processor is happy, this processor is sad. So how do you handle this becomes a problem, actually, because these things happen, especially when you have lock contention, for example, or contention on shared data. These are exactly the issues that are happening. For example, if you think about the synchronization, whenever another processor releases a lock, if it's a contended lock, you can be sure that many other processors are waiting for that lock, right? They're like hungry wolves waiting to attack this sheep that's being released by this processor. And they all are going to request that. And at the higher level, at the synchronization protocol level, there have been many algorithms that are developed to minimize that contention, right? Okay, you assume that you minimize as much as possible, but at some point, actually, at the higher level, in the software level, you can implement structures that ensure that you have some ordering, right, for these locks. Those are called ordered locks, and MCS locks are an example of that. So in the higher level, you can actually have ordering, but that adds overhead into the system also, because now the software is managing the locks, right? You could punt that responsibility to the directory as well, right? You could have no ordering, so you could get a lot of requests, and the directory needs to deal with it. How does it deal with it? Well, okay. But basically, this processor, when it needs the data, it sends a read exclusive request. Now, this processor was granted before, so the directory needs to invalidate it and get the data back, either directly from here or a revision and then through here, right? This is an example over here. This is essentially an acknowledgement saying that I've invalidated my data. But this is not the only way of handling it. So this is essentially contention. Certainly, you need to escape the race conditions by NACking requests to busy entries. So, for example, over here, what the directory did was it NACked the request for this processor. But that's not the only way of handling it. Basically, original requester in this case needs to retry somehow. But that caused additional traffic also, right? You NAC the request, original requester will want it again at some point. Presumably, it was not a spurious request. As a result, you add a lot more traffic. Or the directory can buffer the requests, right? It can queue the requests and grant them in sequence. Now you're essentially helping the synchronization construct in the software level, saying, oh, I have this hardware-based queue, and that queue is granting the requests to different blocks, let's say, or the different shared data. Or you can have a combination of them, right? The key question is, of course, once you have buffering, how big your buffer should be. Should it be 10,000 entries if you have 10,000 processors? That's a lot. And that's, again, for a single cache block, right? You don't want that, perhaps. So it's really a combination of these, usually. But once you buffer, there are also issues over there. How do you actually ensure fairness across the locks, across the requests that are coming to the directory? Yeah, you can see the design space now. Yeah, that's what I said, basically. Which requester should be preferred in a conflict? And also, other stuff matters over here, right? Interconnect delivery order, distance. Maybe some requester is very, very far away from the directory. some other requester is really close to the directory. So you can actually have a fairness issue in the sense that if this processor is always trying to acquire this lock, and this other processor is always trying to acquire that lock, same lock, this processor is inherently slow, right? Because it requires 100 cycles for this processor to make the request to the directory, whereas this other processor is sitting on the same node as where the directory sits. So you have a fairness issue. Even though the programmer doesn't have a fairness problem, the hardware may actually cause a fairness problem because of the distance between the requesters and the directory node. So all of these matter. So you may actually have a nicely written parallel program. You run it on a directory-based multiprocessor, and you figure out that one processor is getting the locks much more often than another processor. And how do you debug that? Well, those are fun issues, basically. You really need to know the topology of your system and how these things are handled. Okay, and ping-ponging, as we've discussed, it can be reduced with either protocol optimizations at the high level, or either protocol optimizations that we have over here. So, for example, if you queue the requests, you can reduce the ping-ponging that happens, right? Or you can have better higher-level synchronization. You can have better locks, for example, combining trees, better shared data structure design, such that you don't have this contention for shared data. In general, it's always good to reduce the contention for shared data at the software level. But we're back to the programmer-microarchitect trade-off, right? If you punt on the programmer and say, programmer, you should handle and you should minimize the accesses to the shared data or the locks, that's a hard thing to do. And now the programmer starts having bugs in their system if they want to optimize the code. Versus we say, oh, programmer, you don't do anything, and I'm going to handle these huge storm of requests to a given shared data or shared lock inside the hardware somehow by doing more complicated protocols inside. Now it's the microarchitect's burden. Now the hardware designer can add bugs into the system, right? So it's a matter of who has better bugs or much easily solvable bugs. Usually the hardware designers. Hardware is usually easier to verify than software because if you think about it, the state space is actually, even though it may be huge, it's more limited than the software in the end, because software can be anything, right? Whereas hardware, you at least have a fixed design, and you can more easily verify it. So it's easier to figure out the bugs in hardware. I said it's easier. I didn't say it's easy. If you order the problems in relative order of easiness, hardware is easier. That's why maybe it's a better trade-off. And also programmers go crazy again, right? If you say that, I'm not going to do anything in the hardware, so you'd better minimize the sharing. So clearly there's a reason for sharing at the high level, right? You need to lock a shared data structure. Okay. So there are a bunch of other questions over here. So I actually dedicate the slide on a topic that's really probably deserves 100 slides or so, but we don't have time clearly. But there are other questions in directory. So how large is the directory is one question. So hardware designer doesn't need to only ensure correctness, but also they need to optimize for space, right? And the directory can actually become really large. And I'll give you an example of this with a reverse engineering problem. How can we reduce the access latency to the directory? So actually, let's do a math over here. If you have, I don't know, how many blocks do you have? If you have a 32 gigabyte memory system, which is really small, and each block is 32 bytes, let's say, that's 1 billion blocks. So the directory needs to keep track of 1 billion blocks. And if you have 1,000 processors in the system, did I do the calculation right? 32 gigabytes divided by 32 bytes, that's 1 billion, right? And if you have 1,000 processors, that's 1 billion times 1,000 bits, 1,001. Okay, we're going to round it down to 1,000. So it's 1 billion times 1,000 bits, 1 trillion bits. That doesn't sound good, right? Okay, so basically you need to optimize the space. How can you reduce the access latency to the directory? As we said, if you distribute the directory, now you're actually making the access latency non-uniform. You run into fairness issues, all of those issues. But also, you can actually run into not so great situations where you have this block, this processor always requesting a particular block, but the directory entry happens to be very far away. So do you cache the directory, and how do you cache the directory becomes a question. And how do you scale the system to thousands of nodes? And can you get the best of snooping and directory protocols? This is still under research. I'll talk about the motivation for an idea called token coherence. I don't think this is the solution, but this is one step toward the right solution in a little bit. But heterogeneity is one thing. You could actually have locally coherent and globally incoherent systems. And then over time, you ensure coherence. So actually, a lot of systems do filtering of coherence messages. You can keep track of things at a coarser granularity. So you can have actually hierarchical systems where you have this part of the system, let's say, consists of 16 nodes. And if you know that the data is within those 16 nodes, you have a bus-based protocol over there. But if you you can have a Bloom filter for a lot of other nodes. And you can say, oh, if I match in the Bloom filter, then I send a request to the directory or some other parts. Right? So you go out only if you have a match in that Bloom filter that says, oh, the data is potentially shared by someone else out there. Now you need to manage the Bloom filters. Actually, these Bloom filters are employed in very large-scale systems, like IBM Blue Gene. When they designed the system, for example, they actually have a lot of filters to filter the coherence messages. So you would like to keep the data local, of course, right? Now you can again punt on the programmer, saying the programmer, you should put the data in this particular part of your multiprocessor, which has 16 processors, because they're nicely coherent with each other with a bus-based protocol. Right? But then you're actually putting pressure on the programmer again. So heterogeneity is very common in existing systems, and existing systems try to filter out all of these requests, a lot of these requests as much as possible. But if your data is not partitioned nicely, if the sharing pattern is random across your entire multiprocessor, then you're back to square one because none of this helps. Right? You always hit in your Bloom filter because somebody else may have the data. Okay, we'll talk about this very, very briefly also. But let me go over a question very, very quickly. This is one example of a reverse engineering question, if you will. This also shows you how big the directory may be, right? So assume we have a processor that implements the directory-based cache coherence protocol we discussed in class, which is what P+1 bits. The physical address space of the processor is 32 gigabytes, and the cache block is 128 bytes. The directory is equally distributed across randomly selected 32 nodes in the system. So the directory is not in all of the nodes in this case. That's what this is trying to say, right? We just select 32 nodes and distribute the directory over there. You find out that the directory size in each of the 32 nodes is a total of 200 megabytes. How many total processors are there in this system? Hopefully this is an easy question, right? So you basically work backwards. So how do we do this? Let's see. We have 32 gigabytes, and you know the block size, and you know that you have 32 nodes that contain all the blocks. So you know exactly how many blocks you have in the system. That's 2 to the 35 minus 2 to the 7, 2 to the 28 blocks. And that's distributed equally across 32 nodes. So each node has 2 to the 23 blocks, right? So let's do that over here. So blocks per node, that's the first thing you compute. And then you know the directory storage per node, which was said to be 200 megabytes. And you could express it this way. Basically, it's 25 times 2 to the 23 bytes, 25 times 2 to the 26 bits. And we know what the protocol is. Basically, we can compute the directory storage per block now because you know each directory node has 200 megabytes. And you divide that by 2 to the 23. As a result, you get 200 bits per block. So basically, each entry in the directory has 200 bits per block. Now, what does that mean? You have 199 processors. Simple. 199 processors gives you 200 megabytes, assuming you distribute the directory across 32 nodes, right? Clearly, we don't have the directory in all of the processors here. Make sense? So, but even this example gives you how big the directory is, right? 200 megabytes is a lot. And this is not a large scale. It's a medium scale multiprocessor, perhaps, right? 199. It's not a lot. And the memory size is you definitely don't want 32 gigabytes for 199 processors. You're very memory bottlenecked in this case, clearly, right? You want perhaps more like 1 terabyte. And if you do the calculation with the 1 terabyte, this shoots up. Okay. Okay. So let's go into a little bit more. I'll finish coherence, and then we'll take a break, and then we'll do the review. I'd like to cover some slides from this token coherence paper that I briefly mentioned, because I think it looks into nice things. It's an old paper, relatively old paper. And we've seen old papers like 1940s here, right? The von Neumann paper that I referenced was 1946. It's not old. But basically, this looks at 3 desirable attributes in a coherence protocol. And you could argue that there may be more, but I think this is a nice abstraction. Basically, you want low latency cache-to-cache misses. You want no bus-like interconnects for scalability. And you want things to be bandwidth efficient. And some of these things actually go against each other. And this paper examines some workload and technology trends. Let's take a look at them very quickly. So they're looking at commercial workloads, but many workloads I think are similar. They have many cache-to-cache misses, and they like clusters of small multiprocessors. Basically, what they want is really low latency in the end. Direct cache-to-cache misses, and maybe moderate scalability. Take this with a grain of salt. But basically, the workloads, if you want low latency, you don't want the directory protocol. Right? That's kind of obvious, hopefully, because you don't want a middleman. You don't want additional indirection. Or you want to have a really cacheable directory protocol, and then you complicate the system. So one of the things that you should perhaps be thinking about is here, where is complexity over here? Now your dimensions become increasing. Okay. But workloads want low latency, so workloads actually would be happier with bus-based Snoopy protocols, right? Okay. So workloads like snooping protocols because you get direct request and response. But snooping protocols violate these 2 things that we want, right? They're not bandwidth efficient because they're broadcasting always, and they require a bus or a virtual bus. But we don't want a bus-like interconnect because it's not scalable. So technology trends, on the other hand, basically say you don't want multi-drop buses like this. So buses are not good because they're not scalable. Because everybody loads the bus, as you can see over here. This is another way of looking at the interconnect. This is called an indirect interconnect, as we will see, multi-stage interconnects. And people used to design multiprocessors this way. When we talk about interconnects, we will see that. So you don't necessarily want that also, because that's costly. And things are not communicating with each other nicely, right? You really have one part of multiprocessors over here, another part of multiprocessors over here. This is really designed for communicating between multiprocessors and memory, if you will. So how do you go from here to here? So it becomes actually very heterogeneous. I mean, this is also heterogeneous, but this is nicer. Now you can distribute things very nicely across things over here. So you really want this sort of low latency interconnect where you can do close communication between your neighbors. So you really want this low latency interconnect as well. This avoids the virtual bus ordering. But this interconnect is good for directory-based protocol. So technology trends actually lead to unordered interconnects. How do you do ordering on this one? Right? You can do ordering on this bus nicely because whenever you broadcast, everybody else sees it. But here, well, you broadcast, okay, maybe you broadcast, you decide to broadcast. Everybody sees it, but everybody doesn't see it at the same time. Right? So you don't get the property of a bus on this one. And how do you make sure everybody sees it at the same time? Well, you need to timestamp things and reorder things, so it becomes very complicated over here. So technology trends actually say if you want scalability, you want interconnects that are unordered like this, that are not good for ordering things. So technology trends say you'd want no bus-like interconnect. So that's good over here, and hopefully it avoids broadcast also. But bandwidth efficiency really comes from the protocol also, so there's more over here. But the problem is, if you have no bus-like interconnect, you have no indirection. You need some sort of indirection, perhaps, and you need some sort of ordering to get. So you don't get low latency, essentially. Okay, so how do you achieve all of the 3 goals? I don't know of anything that actually satisfies us, and this paper doesn't satisfy it either. So they say they want step 1 over here, and they would like to take step 2. I'm not sure if they've ever taken step 2, but I'll talk about step 1 very quickly. But I like the idea. Basically, the idea is they want invalidation-based coherence, and they have an invariant, right? The invariant is really many readers or single writer. And this is enforced by globally coordinated actions. If you have a bus-based interconnect, you enforce it, right? You can either have many readers or a single writer. So the idea over here is to have tokens. Somebody manages the tokens. You have a fixed number of tokens per block. And if you want to write to a block, you need to get all of the tokens. If you want to read from a block, you just need one token. Right? And these tokens travel across the network. Now, how do you manage the token? Becomes interesting, and that's where things affect bandwidth efficiency, right? But now you can actually design a protocol. So I think the biggest benefit of an idea like this is decoupling performance and correctness, as you can see over here. The correctness is really satisfied by this invariant that we have, the traveling tokens, if you will. And you can enforce that with only local rules. The problem is you need to ensure that somebody gets the tokens if they want to write to it, right? You need to ensure all of the other issues that we've discussed, fairness and starvation. How do you ensure that? But maybe now your protocol can be a bit simpler because you just need to keep track of the tokens and manage the tokens. Right? There is no single coordinator, perhaps, that's managing things, although you may need to add it. OK, so that's basically the key insight that I wanted to give you. And that's one of the ideas, one of the many, 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 many ideas that have been proposed for coherence. I don't think this is implemented in any place because there are other issues in managing the tokens, because somebody needs to correctly manage the tokens, ensure fairness, non-starvation. But hopefully it exercises your mind a little bit. So this is where we will stop. Any questions? No questions. Everything is very clear. So. That's good. The good thing is, you know, you're not going to be asked about this in the exam next week. OK, so what I would like to do after perhaps an 8-minute break is, if you have any conceptual questions on any topic, I'll cover those first. And if not, then the TAs will solve some of the questions from the homeworks. Is that a good idea? Let's do it that way. So think about any conceptual questions that you may have on any topic. Hopefully, preferably on the exam, but I'm happy to cover stuff that's not on the exam also. So if you decide to talk about coherence, that's fine. But if you don't have any questions, then we'll just jump into solving problems from homeworks. OK, let's take an 8-minute break now.